Okay, so this is something that's derived in the book, but I think they leave some steps out, so I'm going to record this video to hopefully explain it in a little more detail. So this is 28.3 section, magnetic field of a straight current carrying conductor. And one way we can do this, find this result, which I have written over here and we've discussed in class, is that the magnetic field is mu0 I over 2 pi r around a wire. And you can solve that using Ampere's law, but you can also use this equation we talked about in class, which is called the Biot Savart law. And this applies for all situations. It just mathematically it can become very complex. But in the case of a wire carrying a current, it can be used. Now we don't use it in a vector form. What we do is, if you go over to this drawing on the right hand side, you'll see there's an angle between the wire, the current carrying conductor, and the vector that goes from the differential element dl to the point P, and that's angle phi. And we know that if we have an infinitely long wire, that the magnetic field at a particular distance from the wire should be the same no matter where you are along the wire, because of just symmetry perspective. So what that allows us to do is to look at it in this form and replace this vector cross product with some simpler geometry. So this is on page 926. You can see the picture. So you have a wire which is going up here, and we're going to say the current's flowing in the positive y direction. Away from the wire, we're going to have some point P, and we have this differential element of the wire, dl, and that dl is a distance y from 0, 0 is where where you are closest to the point P in space. We're going to call that distance x. Now, in the equation here we use r, but this r is different. This r, the x and the r are the same quantity. In this case, we use x to define the distance, perpendicular distance from the wire to point P. R is actually the hypotenuse of this triangle, which varies as well as y varies. Kind of like, the related rate problems where we had one side of a triangle being constant length, two of the sides varying, but being related through the Pythagorean theorem. So the same thing is going to apply here. This angle phi is between the wire and the vector. But my triangle here is this angle. So if we take 180 degrees, which is pi radians, and you subtract phi, that's the angle inside this triangle. So we're going to use that angle. But it turns out they're related, which we'll explain in a minute. Now I'm doing this video probably about 2 weeks before you can actually do this problem, because we're going to use something called trigonometric substitution, which at this point you don't know. So this is the non-vector form. So you take dl, which is this differential length, which we're going to say is dy, because this length is in the same orientation as the y direction. So dl is going to be dy. The sine of phi we're going to get from this triangle in a second. R we can also get from this triangle. Okay, so let's go to the next page. So we have this relationship, right triangle geometry, Pythagorean theorem, x squared plus y squared equals r squared. In this case, x squared is fixed. Y and r vary. Now here's a description of the phi. So here's the angle phi. Here's the angle pi minus phi. So if you look at the angle pi minus phi, in the book it just says this is true, but they don't really explain why it's the case. So you could also write this as the sine of minus phi plus pi. We'll see why I'm doing this in a second. And let's move some of these things down. Okay, and then I need to move this back up. Okay, so all I've done here is change the order. Now, you may not have remembered this from pre-calculus, but what I would do is I'd factor out a negative sign. So I'd have negative phi minus pi. So pi minus phi is the same as negative the quantity phi minus pi. So this means there's a y-axis reflection when you have a negative sign. And this is the x shift. So this means I move pi in the positive direction. So let me go up here. I'm going to draw this again. I went through this one time, but then I realized I didn't do it that well. So the first one is just the sine function. So here's the sine, 2 periods. Now, if I move this pi units, so it's positive pi because it's x minus h. H is, so if I draw a green line that goes over the red line, and then I take that green line and I shift it, I get that. So the maximum here becomes a minimum in the same location. So that's this shift. And then if I reflect it across the y-axis, this comes over here and that comes over there. And so now the blue curve, which is this thing, is the same as the original non-transform function, which was the sine of phi. So the red curve was the sine of phi. This showed the transformation of shifting it positive pi units. This negative reflected across the y-axis, and so we came back. So what that ultimately means is that the sine of phi is the same as the sine of pi minus phi. Sine of phi is the same as the sine of pi minus phi. And as a consequence, I can just look at the geometry of this angle. So let's see, this is the angle. The sine of pi minus phi is the length of the opposite side over the hypotenuse. So I can make these substitutions now. So the sine of phi is x over r. I've got r squared already, so I get x over r times r squared. So that's x over r cubed. So let me put this up together, a little nicer format. So I'm integrating to find the total magnetic field at a point P. I'm going to integrate from negative infinity to positive infinity, and I've got mu 0 over 4 pi I sine of phi is x over r, and then r squared is r squared. I replace dl with dy. So I can take out the constants, and with respect to this integration, y, x is also a constant, so I can take that outside the integral. So what I'm left with is 1 over r cubed dy. Okay, so now what we want to do is plug in what. So what is r cubed? R cubed is r square root of r yeah, it's r times r squared. That's one thing it is. But r is equal to the square root of x squared plus y squared. So if I plug that in, that becomes r cubed becomes x squared plus y squared to the third power, 3/2 power. Okay, so r squared is x squared plus y squared. R is the square root of x squared plus y squared. Square root times the thing is to the 3/2 power. So I can replace again, I'm integrating from negative infinity to positive infinity. So what I get is 1 over x squared plus y squared to the 3/2 power times dy. So that's the integral. And you have to use trigonometric substitution for that. So if we come to the next page, we're going to set up the opposite side to the angle theta as y and the adjacent side x. Y is the thing that's changing. X is a constant. So in calculus we'd have like x over 3 maybe. But in this case we have y and x. So it's a little confusing in that sense. So you have the initial substitution. We want to solve for y because that's the substitution we're going to make. For dy, we need dy. So we need to solve this for y. We're not going to actually use this substitution because we don't have any y's by themselves. But if you multiply by x, you get y is x tangent theta. So the derivative dy is x, which is a constant, times the derivative of the tangent, which is secant squared, and then multiplied by d theta. The other substitution is the one that goes with the tangent, which is the secant. And the secant is the hypotenuse over the adjacent. Now normally this is the variable term divided by the constant term, and in this case x is a constant, so it is correct. So you get the square root of x squared plus y squared over x, and if you multiply both sides by x, you get the square root of x squared plus y squared is x secant theta. So I can make that substitution here for, if I cube this, I'll get that. And for dy, I'm going to put in x secant squared theta d theta. So we plug all that in, and because I factored out the x this time, we don't need the x anymore. So for dy, we put in x secant squared d theta. For x squared plus y squared to the 3/2 power, we put in x secant theta cubed. And you can see we have x divided by x cubed, so we get x squared, and then I could factor that out because x is a constant. And then we have secant squared divided by secant cubed, which is 1 over secant. But 1 over the secant is the cosine, and when you integrate the cosine, you get the sine. So that's my integration. Then I can remember what the sine is. The sine of an angle is the opposite over hypotenuse. So I can replace the sine of theta with y over the square root of x squared plus y squared. And let's fix this. These are all squared now. So now I go down here and I can write the results. So I've got mu 0 I x divided by 4 pi. I've got the integral here, which is 1 over x squared times y divided by the square root of x squared plus y squared. And I'm going to evaluate that between y equals negative infinity and y equals positive infinity. Now, I'm just going to do kind of a order of magnitude analysis here. So I'm going to pull out this x squared part, 1 over x squared part, and then evaluate this. So you can see if I stick infinity in here, I'll have infinity over the square root of x squared plus y squared. Well, when y is really big, like infinity, this term becomes insignificant. So essentially this becomes y divided by the square root of y squared, which is y over y, which is 1. So when I plug in positive infinity, I get positive 1. Now when I plug in negative infinity, I'll get negative y divided by the square root of essentially positive plus, this is essentially 0 relative to y, so this becomes plus negative infinity squared. So when you do it at the lower limit, you get negative 1. So I'm subtracting the lower limit, but the lower limit results in negative 1. So I end up having negative 1 plus a minus 1, which is plus 1. So I'll get mu 0 I. This x cancels out one of those x's, so I get 4 pi x, and I get 2 from this. So 2 divided by 4 is 1/2, so I get mu 0 times I over 2x pi times x. But in my terminology that I've been doing, this is the distance from the wire, which we used an r in our original description. So that is it. Hopefully that makes more sense than what's in the book. Like I said, they leave out some of the details. They just say use trig substitution or integral tables. So that's the trig substitution part of it.